Hello, everybody. So this is our last lecture of the semester. So that's kind of crazy that this, how this semester went by. It's definitely going to be one that I will remember for a long time. So hopefully, even though we had to transition to online and we didn't get to see each other anymore, you got something out of the second half of this semester, and you'll be able to carry that forward into organic too. So really just wanted to say, from my perspective, it's been a great semester, even though we had to, move online. There was still, quite a bit of participation through discussion boards and office hours and all that. So thank you guys all for staying active in the class. Okay, so about what we're going to do today. So you'll see what's up on the screen right now, which is there's some naming that we had to take care of for ethers, but then the rest of the class really will be focused on one specific ether, and that's the three-membered cyclic ether, which we also know as an epoxide. So the naming of ethers is largely going to be a do-it-yourself activity. So this is section 11.2. It's literally 2 paragraphs in our textbook on page 493. You can skip the section on cyclic ethers. So I put some examples here just so you could see, a few other examples besides the ones that were in the text. But what you'll notice through these examples is essentially that you're going to name, whatever fragment on one side of the oxygen or the other of the ether, whichever one is shorter, as a substituent. So, and along with that, as a substituent, it doesn't bear any priority compared to the other functional groups that we learned. So if you go back to our functional group priority table, ethers is down at the bottom by alkyl halides. Okay, so we will treat it just as a substituent, and you can see that through these examples. Okay, so what we want to spend the rest of today talking about is going to be epoxides. So when you'll want to pull up the notes here because you'll see that there are some examples for naming, that continue on to the bottom part of that page. Okay, so let's go ahead and jump into epoxides. Okay, so epoxides are pretty important. They serve a synthetic purpose, which we'll see. So a purpose in synthesis that we'll see as we learn the reactions of epoxides. So essentially, we have 4 reactions to cover. We need to cover the preparation of epoxides. We'll have 2 different ways, and then we'll have the reactions of epoxides, which there will be 2 of those reactions. So that's our game plan for today. So first, we're going to start with just some general, our normal. What is an epoxide? What does our functional group look like? So here's our epoxide. Okay, so it's a strained 3-membered ring, which relates to its reactivity. So it's a strained 3-membered ring. And if we relate it to, other species we've seen that kind of look like that, hopefully we can rationalize that it's an electrophile or electrophilic at the carbon atom. Okay, and that's because we have these bond dipoles towards the oxygen, which would put these partial positive charges at carbon. And so we can donate electrons to the carbon and push electrons up into oxygen, kind of like a bromonium bridge or a mercurinium bridge. So several of those bridge species that we saw are similar in their reactivities. Okay, so let's go ahead and think about how we're going to make epoxides. And again, we'll have 2 different ways. The preparation of epoxides. Hey, it wouldn't be lecture if I didn't forget that one last time, but my kids are out of the house, so at least they won't be barging into this lecture. So, all right, so preparation of epoxides. And indirectly, they're both from alkenes, but one is a 2-step procedure and one is a single-step procedure from alkenes. So we'll start with the more common way. So let me go ahead and show you that. Okay, so we're going to start with our alkene starting material, and the easy geometry or cis-trans geometry of our starting material alkene is going to become important because this is a stereospecific reaction, as we'll see. The reagents by acronym is MCPBA, and then we have dichloromethane CH2Cl2 as our inert solvent, and we've seen that solvent several times now this semester. Okay, so what we're going to see is that the 2 carbons of our alkene are going to end up as the 2 carbons that are bound to the same oxygen to make our 3-membered ring. And whatever the relationship is between our substituents, R and R1, or whatever substituents we have, so in this case they're trans, they need to remain trans at the epoxide. So let's see what that would look like for this molecule. Okay, so if R is on a wedge, R1 would have to be on a dash. So we can just make that note here that if our alkene starting material is trans, that the relationship between those groups should be trans at our epoxide. And there's two different ways, two stereoisomers that would give me that trans orientation. They're related as enantiomers. Here's one way that you could draw those enantiomers. Okay, and you can see there's still trans there. So this would be a racemic mixture of those two trans stereoisomers. Okay, so again, if our starting material is trans, that stereochem is carried through in the product. And so we would call this a stereospecific reaction, in that the EZ geometry or the cis-trans geometry of our starting material is going to influence the stereochem of the product. Stereospecific. Okay, so what does that tell you about the mechanism if the cis-trans relationship in the alkene remains in the products? So hopefully you've started to realize some commonalities about some of the stereospecific reactions we've learned. So in the past, when we've had a stereospecific reaction, namely SN2E2, the reaction of BH3 across an alkene, what did all of those reactions have in common? So what they had in common is that they were a single-step concerted mechanism. Okay, so the reason why this reaction is stereospecific is because mechanistically, both new bonds to oxygen are formed at the same time from the same face. Okay, so let me describe to you what MCPBA is. So let's look at its structure. So MCPBA, it's the world's longest name, so we'll go ahead and write that out for fun. So M stands for meta. You'll learn what that means next semester in Organic 2 when you name benzenes, but I'll give you a clue as to what that is when we draw the structure. Okay, so it's meta, chloro, peroxy, benzoic. We haven't gotten the A yet. Acid. Okay, so MCPBA. Okay, so we know hopefully what benzoic acid is just from, learning about functional groups and whatnot. And hopefully we can rationalize what per means. So remember we saw peroxides before, and that was molecules that have oxygen single bonds. And so now what we're going to see for peroxybenzoic acid is that our carboxylic acid is going to be the functional group that contains that per oxygen bond. Okay, so what does this look like? So meta tells us the substitution pattern between the chlorine substituent at benzene and the peroxybenzoic acid. Okay, so this functional group over here, this we could refer to as a per acid. Okay, so a peroxy acid. And peroxy acids are required to do this transformation, alkene to epoxide, but there are other per acids that you could use, where you don't have a chlorine, maybe you have a methyl group, and maybe the distribution around benzene is different, but MCPBA is the most common one. Okay, so one of these oxygens in our per acid is going to be the oxygen that undergoes the reaction with our starting material alkene. Oh, and one last thing I wanted to mention while we're here is some of the ways that we can abbreviate the per acid is RCOOH or RC carbonyl OOH. So if you see an abbreviation like that, you can see that oxygen single bond in the per acid. Okay, so let's go ahead and look at an example, and through that example, I'll quickly show you the mechanistic arrows, although you will not be held responsible for the mechanism of this reaction. But I think it is useful to help us understand the stereospecificity. Okay, so we have metachloro, peroxy, benzoic acid, CH2Cl2. Okay, so what is the EZ geometry of our alkene here? Z, we could also call it cis. So what should be the stereochemical relationship between the ethyl group and the methyl group in our epoxide? Hopefully you said trans, okay, or cis. Sorry about that. So they're definitely cis. The cis starting material gives us a cis product. Okay, so there's one way that the one enantiomer, the other way you could draw, so one way up top we drew the mirror image, another way we could draw the enantiomers by inverting both chiral centers. Regardless, both substituents here are cis and cis. Okay, and this constitutes our racemic mixture. Okay, so if we're going to look quickly at the mechanism, let's account for the stereospecificity. Okay, so we have our alkene starting material, and then we have the oxygen of our per acid. And I'm just going to abbreviate that benzene part as R because it's not important to the mechanism at hand. Okay, so what we're going to see is that the alkene attacks one of the oxygen, or that one terminal oxygen, and then one of the lone pairs on that oxygen comes back and attacks the other carbon. So this is a single step concerted mechanism. Everything else I'm going to draw about the arrows is not super important as, as it relates to what's happening to the carbons of the alkene. But what we see as a byproduct in this reaction, the way that I drew this is going to make it hard for me to draw the arrows, but that's okay. Okay, and that grabs that proton. So I'm going to erase actually some of these arrows because I think they're just distracting. But what I want to show here really is just these arrows. So from one of the carbons of the alkene to the oxygen, and from that oxygen back to the carbon. Okay, and so since this is a concerted single step mechanism, we would retain the stereochem. There isn't time for rotation about this carbon-carbon bond. So one of the most important factors here in this mechanism, it's a single step concerted mechanism, and it's going to account for the retention of stereochemistry as it relates to the easy geometry of our starting material, alkene. Okay, so we looked at one example of a Z-alkene. Let's just look at one more example of an alkene starting material, and then we'll move on. Okay, so there's our alkene. There's MCPBA. Oh, maybe I'll add up here, abbreviated, so we know that we didn't write all the steps. Okay, MCPBA, CH2Cl2. So what I want you to look at is the relationship between two of the groups about our alkene. So we could look at the relationship between this carbon of this ethyl group and that carbon of that ethyl group. We see that they are trans. Okay, so in the product, we should expect the two ethyl groups to be trans to one another. So when we draw the product, okay, I typically am drawing my epoxide in plane. And let's just say I put the ethyl group on the left-hand carbon on a dash. That would mean that the ethyl group on the right-hand carbon is going to have to be on a wedge. And we can show the enantiomer by inverting both those chiral centers. So then we would have the ethyl on the left-hand carbon on a wedge and the ethyl on the right-hand carbon on a dash. Okay, and so we see this as a racemic mixture. Okay, so that's one way that we can make our epoxides. So there's one additional way to make epoxides, which we've actually seen, part of this reaction before, but we're just going to go one step further. So one additional way to make epoxides. And this is indirectly from the alkene as well. And so in this reaction, what we're going to do is we're going to start with the alkene again, but we're going to make a halohydrin. Okay, so remember a halohydrin is the product of electrophilic addition of a halogen, so chlorine or bromine, with water. And so remember in this mechanism, in this reaction, we had a stereospecificity issue, which was X and OH were added anti. We also had a regioselectivity issue, which was that the OH ended up at the more substituted carbon. So those are things you would want to recall, although it doesn't really matter in the overall product of the epoxide because you lose some of that regiochemistry. Okay, so let's go ahead and draw the product. So in this case, I don't have a more and a less substituted side, so I'm just arbitrarily going to put my OH at that carbon and my X group at that carbon. Okay, so what we're going to do is we're going to take that product of halohydrin formation, and this would be both racemic and you'd have another regioisomer. And what we're going to do is we're going to treat that molecule with NaOH. Okay, so what do you think NaOH might do in this reaction? Well, notice that we have an acidic proton in that alcohol. So what would happen if I deprotonated to make the alkoxide? Okay, so now I have an alkoxide on the carbon adjacent to my leaving group carbon. Okay, so we learned of a substitution reaction last chapter that involved, or 2 chapters ago now, that involved a strong alkoxide nucleophile and an alkyl halide. So what we can see is an intramolecular SN2 reaction. So our oxygen atom could attack that carbon and the leaving group would leave. That would give us our epoxide. So this is intramolecular SN2. Okay, and so if we wanted to show the stereochemistry on the epoxide now, we could do that. So the oxygen came in from the top face, so we could draw that in that way. It would also make sense, another way you could draw this, and this would be racemic throughout. So the other way we could draw this is to put our epoxide in plane, and the net stereochem is retention from the starting material. So if our R and R prime or R1 are trans in the starting material, they will end up trans in the product, just like MCPBA. So from the starting material alkene, these two methods are equivalent. Okay, so if I would have taken the starting material and reacted that with MCPBA and CH2Cl2, there I have the same products. Okay, so in essence, what we're doing here is an intramolecular SN2 reaction. So let's just look at an example or two, and we can, see how it's an equivalent method to starting with the alkene and doing MCPBA. All right, so let's look at this starting material, and we'll do Cl2 and H2O. Okay, well, the regiochemistry that we learned was going to be that the OH would end up at the carbon that better accommodated the positive charge. And we don't need to show this stereochem at the carbon where the chlorine is. This would be racemic at this point. And then what we could do is treat with NaOH. And you could use other bases here, like you could use potassium hydroxide. The counterion to hydroxide is not super important. Okay, so we would form that alkoxide anion, and we would do the intramolecular SN2 to form the epoxide, and it would be racemic at this point. So we could draw the other stereoisomer as that bond to the epoxide being on a dash. Okay, we don't need to show the stereochem at this carbon because it's not a chiral center. And if you felt more comfortable, showing the two bonds of the epoxide in plane like we had before, that's fine. Then just put your methyl or your benzyl group, phenyl group rather, your benzene on either a wedge or a dash to get your racemic mixture. Okay, so this would be racemic. Okay, so and lastly, we can just say one more time that if I were to treat the starting material with MCPBA, I would get the same reaction mixture. Okay, so you should be comfortable using either method, but either method should give you the same products from the same starting material in terms of what epoxides you're arriving at. Okay, so what we're going to talk about now is the reactions of epoxides. So I mentioned we generally have two reactions to consider. Okay, and there are two general reactions, not with specific reagents, but general, like SN1 and SN2 are general mechanisms. Okay, so essentially, both of the reactions we're going to learn are epoxide opening reactions. The difference between them is whether we're going to be in acidic conditions or in basic conditions. Okay, so let's get a heading on here. So reactions of epoxides. So the first one is going to be acid catalyzed ring opening. So acid catalyzed epoxide opening. So these are reactions that are going to be done in the presence of acid. So here you want to think are SN1 type conditions. So weak nucleophiles, and we typically have then a proton source. All right, so let me just give you the overview of what we're going to expect in this reaction. So we're going to take our epoxide and we're going to react it with H2O and some sort of H+. Okay, and this could be HCl or H2SO4. Really, strong acid is what we're looking for there. Okay, but it could be other acids as well. And water, what the role that water is going to play is going to be as a nucleophile. So we had already talked at the beginning of this section that epoxides are electrophiles. So in this case, our water is our nucleophile. So the product of this reaction is going to be dependent on the nucleophile, but if water is our nucleophile, we end up with a diol. Okay, and so I want to look at the mechanism for this general reaction scheme, and then we'll increase the substitution or change the substitution pattern at the epoxides. We'll give the epoxide carbons some substituents, and then we'll talk about things like regiochemistry and stereochemistry. Okay, so let's look at the mechanism for this acid catalyzed opening. So when we have weak nucleophiles such as water, it's not strong enough to attack the epoxide carbons directly. Okay, so we have two options. We could make our nucleophile more nucleophilic. And in this case, that would be under basic conditions. So the stronger version of water as a nucleophile would be hydroxide. But we're under acidic conditions. So if we're not making the nucleophile more nucleophilic, our other option is to make the electrophile more electrophilic. And this, difference in facilitating the reaction under acidic versus basic conditions is something you're going to see like probably 55 times next semester, which is under basic conditions, you are typically making the nucleophile more nucleophilic to facilitate the reaction. In acidic conditions, you are making the electrophile more electrophilic. Okay, and that's going to be through protonation. All right, so what we're going to see is that we're going to use the product of H2O and H+, which would be hydronium. Okay, so we're going to use hydronium, and we're going to protonate our epoxide. And we're going to see that that serves the role of making our epoxide more electrophilic. All right, so why would it be more electrophilic? Well, now I have an oxygen atom with a plus charge. So it increases the polarity of that bond, or the differential in the electronegativities. And so it actually increases the positive charge character on the carbons, making it more electrophilic. Okay, so this protonated epoxide is more electrophilic than the neutral epoxide, and that happened through protonation. Okay, so now I can take my weak nucleophile, and in this case, both my carbons of my epoxide are equivalent. So I'm going to take my weak nucleophile, which is water, and I'm going to attack that carbon. And then I can't stop my mechanism there, so I'm going to give those electrons to the oxygen that has a positive charge. So what I want you to think about here is, remember these old friends of ours, bromonium, mercurinium ion. Notice how this protonated epoxide is similar. It has a heteroatom with a positive formal charge, and then it's a bridge to those two carbons in a three-membered ring. So the reactivity of this protonated epoxide can be compared to bromonium or the mercurinium ions that we have already talked a lot about this semester. Okay, so the product of this mechanistic step then is almost the diol, but we have its conjugate acid. So the last step then would be to deprotonate and create our neutral species. There it is. Okay, so we have our diol. All right, so we had already mentioned that protonation makes the epoxide more electrophilic, and that allows for the weak nucleophile to attack. We also talked about how bromonium and the mercurinium bridge species are similar to our protonated epoxide. Okay, so keep that in the back of your mind as we move forward. So some things we still need to talk about are regiochemistry. What if I have a more and a less substituted carbon in my epoxide? And then also some stereochem issues. We'll do that through examples. Okay, so another example I want to look at is just to point out that these are general conditions under acidic conditions. So here is my alcohol, or some other weak nucleophile. And so think about our SN1, E1 nucleophiles that we used. Those are really the species we're looking for here. Okay, and then we have that under acidic conditions. So now the species that is going to attack at this point is going to be ROH. So instead of forming a diol, I'm going to form an ether on one side and an OH on the other side. Okay, so the products of this reaction will look like this. Oops, that's not selected, but it erased anyway, so let's try that again. Okay, so what we're going to look at next then is, let's actually use that to our advantage, now that we have this differential between the two sides, or the two carbons of our epoxide, to track the regioselectivity. Okay, so what we're going to look at is an epoxide now that has a more and a less substituted carbon. Okay, so if you're thinking about bromonium, all right, as a surrogate. So if I was going to have a nucleophile attack bromonium, so let's just say water was going to attack bromonium, which carbon would it attack? The more or the less substituted carbon? Hopefully you said more, okay, which is true. All right, and so we're going to follow that same regioselectivity in this reaction. Okay, so if I reacted this with methanol as our weak nucleophile, and we have acidic conditions like H2SO4, our intermediate would be our protonated epoxide. Remember, we do that, mechanistically, it's rationalizing formation of a more electrophilic species. And then we're going to have methanol, CH3OH, as our nucleophile. Okay, so methanol then is going to want to attack the more substituted carbon. Okay, so why would it want to attack the more substituted carbon? Well, because that carbon can better accommodate a positive charge. Just like when water attacked the more substituted carbon of bromonium. We talked about how that more substituted carbon had a more electrophilic character because essentially hyperconjugation. And so similar thing here. Okay, so the other thing that's important is what happens to the stereochem at the carbon that we are attacking. So the first thing we can write is we're going to attack the more substituted carbon. Okay, and that's because it's more electrophilic. And then the other thing is we invert the stereochem. So we invert the stereochem at that same carbon. Okay, so the carbon that's attacked, we invert the stereochem. Because if you were to look at this mechanism, the oxygen attacks and essentially the electrons of what we could call a leaving group leave. That happens in a single concerted fashion. This is really an SN2 type substitution at that carbon. Okay, so let's go ahead and draw the products there. Okay, so the nucleophile that was added was methanol. Okay, and how could we show inversion? So just like when we used to show inversion at these bromonium bridges, I'm going to do that in a similar way. So when that methyl group kind of flips to the top, that correlates to inversion of configuration. Okay, so let's just make a note there that that methyl group inverted. Inverted. Okay, so through this example, we've tackled both the regiochem and the stereochem. All right, so what I want to do next is, what if our other carbon, the carbon that doesn't get attacked, so if this carbon has a substituent, what happens in that case? Okay, so let's look at one last example under acidic conditions, and then we'll switch gears and talk about basic conditions. Okay, so here we'll have two substituents, and then one substituent on the other side, and then let's react it with water. Okay, so here we'll be able to track the regiochemistry through the stereochemistry, essentially. Okay, so if we were to generate our protonated epoxide as our enhanced electrophile, then we're going to have water as our nucleophile. Okay, so which carbon would you expect water to attack? The carbon on the left or the carbon on the right? So hopefully you said the carbon on the left because it's more substituted. Okay, so notice how we're not affecting the stereochem at the less substituted carbon. Okay, so we do inversion of configuration at the more substituted position. And by the way, I'm putting those double arrows there because we are, we're not really completing the entire mechanism, but there was one mechanistic step, which was deprotonation, that we're not drawing. Okay, so the inverted product would still have the benzene on a wedge and the methyl group on a dash, but now they've flipped up to the top hand side of that molecule. Okay, so that correlates to inversion. The other thing I want you to think about is, what is the relationship between the diols here? Does that look like syn or anti? So it's anti, right? So actually, opening of epoxide allows us to get to a 1,2 anti-diols, which is opposite from OSO4, which gives us 1,2 syn diols. Okay, so this would be an alternative method. And we're actually, I think we'll see that when we look at under basic conditions. Okay, so the highlights of under acidic conditions, first is we protonate to make the epoxide more electrophilic, then our weak nucleophile can attack. Things we're looking for as the weak nucleophile would be, water, alcohols, and generally other weak nucleophiles we saw back in SN1. And then lastly, we attack the more substituted carbon, and that carbon undergoes inversion of configuration. We're going to see some similarities, but also some differences when we talk about epoxide opening under basic conditions. Okay, so our second reaction under this is epoxide opening under basic conditions. Okay, so here what we're going to be looking for is strong nucleophiles, which are generally strong bases. So instead of having water, we're going to have hydroxide. And then we're going to see that requires a second step in the reaction, a workup step, for reasons that we'll see. Okay, so let's start with the same generic starting material. So that with no substituents is called oxirane. So we'll use NaOH, and then we're going to see that we have to have some sort of H plus workup. Okay, so that could be, you could write that as HClH2O, H2SO4H2O, trace acid, but basically we need a proton source, and we'll see why that is in the mechanism. Okay, so under acidic and basic conditions of epoxide opening, in some cases we actually can't tell the difference. So this product is the same as what we drew for opening under acidic conditions a few minutes ago, but we're going to see that there is a regioselectivity difference under basic conditions. Okay, so let's look at this first, this straightforward mechanism, and then we'll, through examples, build in complexity. Okay, so I had mentioned that under acidic conditions, the role of the acid was to make the electrophile more electrophilic. Well, the role of the base, which in this case is also our nucleophile, it's hydroxide, is essentially to make the nucleophile more nucleophilic. I hope we can all rationalize that hydroxide is a better nucleophile than water. It has an excess of negative charge. And so it actually being a stronger nucleophile can directly attack the electrophilic epoxide. I don't have to first activate the epoxide. Okay, so in this way, I can have my nucleophile, hydroxide, directly attack the carbon. Okay, so the strong nucleophiles directly attack the epoxide. I don't have to first protonate. Okay, and so that gives us actually the product of step 1. So this is the product of step 1. So the step 2 conditions are going to be the H+ workup. Okay, so let's just assume we made hydronium in some way through that workup step. And so the last step then is going to be to protonate our alkoxide that we generated and bring us back to our neutral product that we observe. Okay, so let's talk about stereochem and regiochem through examples. So our first example, let's look at this. So we'll have step 1, we'll use methoxide, sodium methoxide, and then in step 2, we'll use HCl, H2O as our workup step. Okay, so here is one of the main differences between ring opening under acid and ring opening under basic conditions. Okay, so under basic conditions, our nucleophile directly attacks our epoxide that is neutral. And so now we're going to flip the regioselectivity. So methoxide being the strong nucleophile favors unhindered electrophiles, just like in an SN2 reaction. Okay, so think SN2 nucleophile likes the unhindered carbon, the less substituted carbon. So in this case, when our methoxide nucleophile attacks, it's going to attack at the less substituted side. Okay, so attack less substituted side. Okay, so we're going to attack the less substituted carbon when under basic conditions. So this is a flip of the regiochem as compared to under acidic conditions. Okay, and we'll also see through an example that if we had a stereocenter at that carbon, whatever carbon is attacked undergoes an inversion of configuration. So we'll see that here through examples in a minute. Okay, so let's go ahead and draw the product of this. Okay, so at the more substituted side, I have my, well, I guess I don't need to show the stereochem at this carbon. I'm going to get rid of that because it's not a chiral center. 2 methyl groups are the same. Oops. Okay, so we can see we have an OH at the more substituted side and our incoming nucleophile, which makes a methyl ether at the less substituted carbon. All right, so let's look at another example of this. So let's look at an example where we have a chiral center at the less substituted side. So let's use this same methyl, phenyl, methyl substituted epoxide. And this time, let's do one of our sulfur anions as our nucleophile. Okay, and then we have our acidic workup. All right, so we're going to see S- as our nucleophile. That's going to attack now the less substituted carbon, and this would go by inversion. So again, whatever carbon we attack, as this is basically an SN2 mechanism, the sulfur anions attacking the carbon opposite of the leaving group, which is the bond of the oxygen and the epoxide. So we get inversion at whatever carbon is attacked. And in this case, that would be the less substituted carbon. Okay, so we can see that methyl group there would be flipped up to the top. That corresponds to inversion. The carbon that we didn't touch, the more substituted carbon, that stereochem is retained in the product. Okay, so let's make a note there, inversion at the carbon attacked. Okay, so the last note I want to make here is, so why is it that epoxides are useful in synthesis? Well, it's because we are basically making a new bond at carbon, and we retain that OH from the original epoxide. Okay, so one thing that I want to write is just let's think about some nucleophiles that you could see in these base opening epoxide reactions. Okay, so nucleophiles for basic ring opening. Okay, and so what I want you to think about, so think about strong SN2 nucleophiles. Okay, and we just had this exam, right? So hopefully this is fresh in all of our minds. So let's think about some. So we've seen a few. So alkoxides, hydroxides, sulfur anions, nitrogen anions, cyanide, azide. What else? Here's a good one. Acetylide. Okay, so etc. There's lots of good nucleophiles we could use here. Basically the same players we saw in SN2. Okay, so I did want to look at one last example to compare and contrast what I'd said before about antidiols. Okay, so I wanted to just look at one cyclic example so we could see that. So I wanted you to recall the reaction with OSO4. Okay, so OSO4 also came with H2O2 and H2O. Remember, this is how we made syn diols. Okay, so I want to point out that if we go through the epoxide route, so let's say we used MCPBA to make our epoxide. There it is. And then we did ring opening under either acidic or basic conditions. Let's just keep it simple and do it under basic conditions because that's what we're talking about. So when that OH attacks, and in this case, it doesn't matter which carbon it attacks from the opposite side of what the leaving group is. The leaving group is our epoxide bond. So if our epoxide's on a wedge, the incoming OH would attack from a dash, and notice how we would get the antidiols. Okay, so we would have a trans relationship between the two OHs of our diols. Okay, so here we ended up with cis diols, here we ended up with trans diols. And in fact, this would be racemic because we could have attacked either carbon of our epoxide. Okay, so that might be useful from a synthesis standpoint, knowing, if you needed to make a cis versus a trans diol, or the stereochem of the diol was, of the two carbons that had the OHs was important. If one of these methods isn't giving you the right stereochem, try the other method, and then you could continue in your synthesis. Okay, so I think the last thing that I want to do maybe is just look at an example of epoxides in synthesis. So let's see what I've got here. So here I'll just do one example, and it'll be like our last kumbaya moment where we do synthesis together. Okay, so synthesis. Hopefully you're not just like tears streaming down your face because of the end of organic chemistry #1. Okay, so what synthesis do we want to do here? Let me pause really quickly just so I can find a good synthesis that's worth our time, and then I will come back and we will work through it, okay? Okay, everybody. I actually wanted to do one synthesis from the workbook. It was a question that came up in office hours several times. And after I thought about it some more, I realized that, I went through this really long-winded way of this synthesis number 10A in the workbook, but actually it was meant to be an epoxide synthesis problem, which will simplify our lives a lot. So I want to go ahead and look at that. All right, so how are you going to realize that you're doing some sort of epoxide reaction in synthesis? So what you're going to look for is a functional group that is either an alcohol or something derived of an alcohol. So that could be the alcohol itself, it could be an ether, it could be a carbonyl through oxidation. So look at this carbon. And then notice how on the adjacent carbon, I've created a new bond, specifically a new carbon-carbon bond. Okay, and that, whatever the new bond is that we're making at that position, one away from the OH, it doesn't really matter, whether it's a carbon-carbon bond or an oxygen-carbon bond, because we have lots of different nucleophiles that can be used. So what this is telling me is that I used a carbon nucleophile to open an epoxide, and the structural result of that is to have a new bond, in this case a carbon-carbon bond, one carbon away from the OH, or some functional group derived of OH. Okay, so if we were going to start the synthesis then, we basically need to make our epoxide. So we know that if we're starting with an alkane, we'll start with Br2 in light. And if I want to make an epoxide, I need the alkene. So I'll do some sort of E2 here. I'm going to go ahead and do it with a bulky base because that will give us exclusively for sure the E2 product, and you don't even have to think about SN2, what conditions are right for E2, and there's no difference between Hofmann and Zaitsev. Okay, now we can make our epoxide. Okay, so there's our epoxide, and now we're actually not too far away from the final product. So what carbon nucleophile allows us to add 2 carbons? So it would be acetylide, right? So we're under basic conditions. We'll have our acidic workup. And this will get us to the observed stereochem. So I could actually attack the top or the bottom carbon. So either the top or the bottom carbon of our epoxide. That's how we're going to get to a racemic mixture. But when that acetylide comes in, it's going to attack from the opposite face of our epoxide. Okay, so we get inversion of configuration at that carbon that we attacked. And now we're actually just one step away from the product, right? So how am I going to convert that 2-carbon alkyne chain to the 2-carbon alkane chain? So I just need H2 and my favorite transition metal catalyst. In this case, we'll use palladium. Okay, so you should compare this to the synthesis that was presented in the workbook solutions, and you'll see that this is quite a bit more straightforward, and it overcomes some of the limitations of that originally worked out synthesis. Okay, so our next synthesis and our last example for all of Organic 1 is going to be this synthesis. And this one's pretty similar to the last one. I just wanted to point out how you're going to recognize these epoxide opening reactions. Okay, so again, I have my OH on a carbon, and 1 carbon away, I have a new bond. So a new OC bond, 1 carbon away from my OH. That tells me I had an epoxide, and in this case, I use methanol or methoxide to attack the epoxide. So the front end of the synthesis, we're just going to make our epoxide, so Br2 in light, as we're starting with an alkane. I need to make my alkene. In this case, I have to use a non-bulky base, so NaOH, H2O, and heat to facilitate Zaitsev. Then I want to do my epoxide, and again, you could use either MCPBA, or you could use the 2-step route that we talked about in class today. And so that's going to give me my epoxide. So it will be racemic at this point. So this is a racemic epoxide. And then since there's no difference in the more and less substituted side in this epoxide, in other words, both carbons of the epoxide have a bond to a methyl group, it actually doesn't matter if you operate under acidic or basic conditions here. So for this one, let's just do acidic conditions. So CH3OH methanol and H2SO4. Okay, and that would give us the stereochem that we've seen there. And since our epoxide going in is racemic, our molecule coming out is racemic as well. Okay, so hopefully you can do some synthesis practice for epoxides. There's a few examples in the workbook. I will go ahead and update the chapter 10 workbook problems in terms of their solutions, because that is where the chapter 11 practice problems were in the workbook. All right, well, good luck on your guys' final. It was, again, a great semester, and I hope some of you guys will actually come back and stop by and say hi when we can actually, be on campus at the same time. So, yep. See you guys all another time.